Okay, welcome back. Today we're going to talk about conjugates, conjugate pairs, their properties, and how to use them. Okay, so we're going to talk about the properties of conjugates, and then that's going to help us as far as using the conjugate zeros theorem, and we can find what we call conjugate pairs. Okay, so we're going to start with properties of conjugates. So again, just for notation purposes, this bar over these letters means we're going to talk about the conjugate of something. Okay, so the conjugate, for example, when we talk about complex numbers, if I have z equal to a plus bi, well then the conjugate, which we would denote by z with a bar over it, is equal to a minus bi, and these are called conjugates of each other. Okay, so if z is this complex number, then we represent the conjugate by the bar over it. Okay, so that's just a little bit of notation. So now, in the properties here, it says for any complex numbers, c and d, right? So any complex number would have something of this form. Okay, so any complex number c and d have the following properties: that if the conjugate of the sum is equal to the sum of the conjugates. Okay, so let me say that again. The conjugate of the sum, so we take the sum of two complex numbers. If we take the conjugate of that sum, that's the same as if we take the conjugate of each number and add them. So what we say is the conjugate of the sum is equal to the sum of the conjugates. Also, the conjugate of the product of two complex numbers is equal to the product of the conjugates. Okay, so these are both the same. And the last property is that we can take any conjugate raised to a power, right? So any complex number, we can take any complex number raised to a power and take the conjugate of that. That's going to be the same as if we move the conjugate inside the parentheses. So we can take the conjugate of the complex number and then raise it to the power. So the conjugate of the power is the same as the power of the conjugate, if you will. Okay, so all this is saying is we can move the bar inside and then take the power outside. Okay, and so that's the properties that all complex numbers hold. Now, we use these properties to prove the conjugate zeros theorem, which I'm not going to do here. It's in the textbook, but again, it's not needed for understanding what we're going to be doing next, okay, at least for this class. Okay, so the conjugate zeros theorem says that, hey, if I have a function that defines a polynomial function that having only real coefficients, okay, only real coefficients, and if z equals a plus bi is a zero of f of x, where a and b are real numbers, then the conjugate of z, which is a minus bi, is also a zero of the polynomial function f of x. So that means that if we find that if we have a complex number, right? So basically what this is saying is if we have a complex number, and we know that a complex number is a zero for a given polynomial, then we automatically get the conjugate as a zero as well. So that's where we get conjugate pairs. So if we know one, we get the other automatically for free. Okay, and that's going to help us factor polynomials, as we're going to see in the next example. And that's it. If you have any questions, please let me know.